Today, I'm going to be talking about GitHub as a cloud portal for reproducible research. This is kind of work that I've been doing in collaboration with several folks at University of Washington. I have this great opportunity where I work at the eScience Institute, which is a data science institute at the university, to work with a bunch of students and faculty across departments. And so a lot of this work is showing some collaborations that we've had and work that others have put a lot into over the last couple of years. So I'm really excited to show some of this stuff and get your feedback. So what is this going to be about? I think it'll be maybe a little longer than 15 minutes. But what I want to do is showcase what I think are some interesting scientific results and how for this particular study, we relied on GitHub Actions to process satellite data. And then to think about what systems others, you all on the call, are using or see others using for batch processing and workflow management in this community. So some other alternative titles I thought about for this presentation were unorthodox uses of GitHub Actions and also making the most of 60 laptops, free laptops, which I think you'll see as this progresses. But those are the main ideas. And so where I see batch computing being useful, there are a lot of options for how to set up batch computing. We were running a lot of workshops at University of Washington, which relied on Jupyter hubs to get everyone onto the cloud working regularly. And this has been essential for like the Pangeo community over the years, is really focusing on Jupyter Hub. But I kept seeing people doing all kinds of things to like run batch workflows on a Jupyter Hub. And my favorite is captured by the screenshot in the lower left, where one of the participants just left a rock on their space bar to keep the kernel active and run something overnight so that it would be ready in the morning. And this is great. I mean, it's a geology focused workshop, so it's particularly great solution in my mind. But there's some need for both the interactive computing that Jupyter Hub provides and then something else to provide the sort of batch workflows that I think a lot of people need. And GitHub Actions, I originally thought of, and I think a lot of people still think of, as just a system for CI/CD, continuous integration, where we're just testing code changes to make sure that the tests don't break. That's like the number one use. It's a great use. But there's more that you can do with GitHub Actions. And so this quote here is actually just taken directly from GitHub's documentation. And I think it's important to emphasize that they say you can use this tooling to run completely customized workflows, any job you'd like. So how does this system work to run batch computing? Just as a brief kind of timeline and background to bring everyone up to speed, I think it is important to understand that GitHub Actions are running on Microsoft Azure. So what I'm going to kind of suggest throughout this presentation is you can use GitHub as a portal to Azure for kind of a small subset of Azure computing. And it's much friendlier than the Azure portal, which we've also used a lot in a lot of projects here. But back in 2018 is when Microsoft bought GitHub. GitHub Actions has been around since a few months after that. And since then, there have been a number of important kind of changes over the years that keep moving this whole platform to resemble more of what I think is a cloud computing platform. So in 2023, you have this ability to connect any GitHub organization to Azure accounts to meter all your expenses in GitHub to an Azure account. So that means you can use what GitHub offers for a charge. So they're larger runners that you can use in GitHub Actions, larger machines. You can pipe that spending through any Azure account. You can set budgets and other things through the GitHub side of that interface, and then everything just gets passed through to Azure. Also in 2024, they started adding more machines, so like GPU machines that you can use on runners, and they increased the the resources available even on the default machines. So in 2024 is where personally in some of my collaborations at the university started to think, we can do a lot of what we're currently doing on laptops, like much more efficiently if we just farm out some of these scripts and computationally expensive but not too complicated workflows onto GitHub Actions and just use it as sort of a batch system. In a little more detail, just this connection with GitHub and Azure. I think a neat fact is that anyone with a GitHub account, which you can get for free, means you can access kind of this base level set of permissions to run GitHub Actions. I'll go over what the kind of quotas are a little bit later, but anyone with a GitHub account can use this setup, and that's really powerful, especially for workshops and just getting people started. And I think structuring workflows with small teams in the system is great as an introduction to cloud computing, where you start to learn patterns of portable environments and then designing whatever workflow you're doing to be ephemeral, to take advantage of cloud resources that are available temporarily, and then just start thinking about storing only critical outputs. So this is my personal kind of opinionated short list of desirable features of a batch computing system. This is sort of the list I go through if I'm looking at an option. And there are many options out there. But what I want to see, and some of this I think is a little bit specific to maybe academic groups, is that you don't need to put down a personal credit card to figure out how the system works. I think that's super important. Really want to be able for the system to just scale to zero. I don't want to have to manage any server that needs to be up all the time for a team to access. And then there needs to be a programmatic interface to it, some sort of secrets management, because even free data providers are often needing tokens and things to set for your workflows. Ability to rerun workflows and some sort of dashboard to view the progress of things is nice. And then team management with various permissions. Who has permission to run those workflows? Is it easy to set those permissions? All of those things, I would say GitHub Actions provides. And then the last three, less so, but sort of. So one is an ability to scale really large. That's something this community has been really interested in for a long time and is important, but I would argue is maybe not that needed for many, many, many research projects. That's sort of the last step and further down the line. And when people are getting started, they certainly don't need scale. The next one is easily selecting a cloud provider or specific data center. With GitHub Actions, with a bit of fussing, you can run things in specific Azure data centers. So we've done stuff like that to work in the same data center where Planetary Computer's hosting their data, but you cannot run Actions easily on AWS or Google without some third-party interface or additional service. So that's sort of a drawback. And then finally, this is very specific to GitHub Actions. So it is nice when you're developing something that you can easily run on different systems. If GitHub's down, then you can't do this. You're out of luck. And that certainly happens fairly regularly, but I would say less so than relying on some of the institutional HPCs we have, or even some of the computing options from federally managed HPC systems. So as I mentioned at the beginning, I want to emphasize sort of where this work came from and emphasize a bit of the research first that motivated this project. In 2024, I was working with Quinn Brencher, who's actually finished his PhD recently at the University of Washington in civil engineering. And he was working to study how glacial moraine dams are moving over time because they present a significant hazard. In particular, there are many glaciers in Nepal that are receding, and this image really captures it well. You can see as these glaciers recede, they leave behind these quite large lakes that are dammed by glacial moraines. These moraines are really unstable dams, and if you can monitor with satellite measurements how those dams move over time, that gives important insight into the risks associated with each dam for potential flooding or failure of those dams. So we used synthetic aperture radar for this study from the ESA's Sentinel-1 mission. I won't really go into a whole lot of detail about how this sensor works, but it is observing continuously, globally, and on the ground, you have what are called bursts from this radar satellite. It's an active sensor that sends out a pulse of microwaves that come back to the satellite. And every time that that's done, the satellite has such a stable orbit, these bursts of information come back in exactly the same place. So you can stack up these image time series really effectively. They cover about 80 kilometers by 20 kilometers on the ground. So it's really like a nice footprint to study these features, these moraine dams that are kind of on the scale of a kilometer or less. So what we did was construct image time series. So you take image pairs from this Sentinel-1 radar satellite, and quite similar, but with a bit more kind of processing magic to how radar guns work when you're measuring speed. You can measure these images over time to construct displacements over time or velocities over time of the ground surface. So what we're measuring here, or what I'm showing in this plot, is sort of the end of the full processing pipeline, is looking at displacements, so vertical change of this moraine dam feature over time. And what goes into this final image is thousands of these image pairs over about 7 years. So we use GitHub Actions to process all of these image pairs. And each of those steps, each of those image pair processing steps takes about 10 minutes. But we relied on GitHub Actions to just scale that out to parallelize it and finish these jobs in an hour or so's time. And then, yeah, as I mentioned, there's a link in the notes to the slides, in the Pangeo notes to the slides. So if you want to access any of these resources like the paper or GitHub repositories, the links should all be in the slides here. So then let's talk about the workflow and how this actually gets done. I mentioned that we take these image pair time series. So we structure a single job that works on an image pair, but then we want to do hundreds of pairwise combinations for each year. So we structure kind of a hierarchy of workflows. 1 year searches the NASA archive to find all the images required in that year, and then farms out to another job all the pairwise combinations to process each pair. So a job is processing 1 image pair. That takes about 10 minutes with software that's been around for a very long time, Python software called ICE. On GitHub Actions, you can run 60 concurrent jobs. So that equates to about 6 jobs per minute. And for this particular project, we're looking at about 750 images that we need to create. So that takes about 2 hours to complete, which for us was a very reasonable timeline to be working with. And then the outputs from this workflow, each image pair processing pipeline generates a folder that's about 300 megabytes of images. And so in total, for each of these bursts, we're looking at 225 gigabytes approximately of outputs that we need to keep track of in order to kind of generate those figures for our final analysis. And so this workflow, ultimately, we were copying the necessary outputs to AWS S3, which I'll touch on later. So schematically, how this works, again, we have this hierarchy of workflows, only 3 of them. So the first one is to process a single image pair. And if you've seen the GitHub Actions before, I'm not going to walk through the syntax, but it's a YAML file. And in that YAML, you specify different steps that are pretty common across like running a Python script, which is what we're doing here. So you check out the repository with the needed code. You set up an environment. We use Pixie for that. You set credentials if they're necessary. So for us, we needed to save outputs to S3, and then you run your script. The sort of batch processing comes through with using reusable workflows and matrix jobs in GitHub. So for that, we create 2 new workflows. One, time series workflow. And I mentioned this briefly earlier. I'll show this again in the next slide, but that needs to search the data provider and finds all the images for a particular year and then put together the combinations of pairs you need to process. And then you can go a step even higher and say, if you want to do multiple years, set up another workflow that calls that one, etc. So you can see how this sort of cascades into quite easily working with thousands of images at a time. This farming out of workflows is done with matrix jobs that really, if you look at the repo and see how these are structured in more detail, it's setting environment variables. So to each workflow, you can pass inputs, and the inputs that are needed are, in our case, we wanted to name the workflow and then the names of the input images that need to be passed to this script to actually run processing. And one of the properties I mentioned earlier is having an API. So you're not always going through the GitHub interface, and the GitHub CLI permits this. So for this example, again, here I'm specifying the repository on GitHub, the workflow name that I want to run. So this example here is running a time series of images for a full year. So the input, we need a year, and then we need an ID of the bursts from that satellite that I showed earlier. This workflow will then go search NASA's archive and call using this workflow call syntax that GitHub Actions provides, the sort of pairwise definition of how to actually process each image. So I'll note that if you copy this command, if you're following along the slides and just paste this into your terminal and run it, it won't work because you need to have write access to that repository to run the workflow. So this is actually, I think, kind of a neat thing. You sort of get authentication to your workflow system for free through GitHub's authentication system. So for your team, if you create a public repository, it's only people who have write permissions that can run the actions and workflows there. But with collaborators, it's very easy to kind of share this workflow and make it reproducible. You would just need to fork the repository such that you have permissions on it. And then if you run this and point in the repository here where the CLI is pointing this -r to your fork, it would run in your repository and should work. In this case, you do need some credentials to download NASA data. That's the only thing that you would have to add. And there are instructions in the repository on how to do this. So what does it look like in the web interface once you've run one of these time series workflows? The interface is pretty nice for seeing logs. So here is a screenshot from GitHub where I'm under the Actions tab. Here at the top, because of the way we've structured our workflow, we've given a name that corresponds to the burst ID we were working with. And then each of those image pairs that the workflow creates is a separate job in the interface, so it's all underneath that single workflow. I honestly get confused with job workflow names on GitHub. I find keeping them straight this somewhat difficult to keep track of. But in any case, the interface is pretty nice. You can see that everything's captured in the same kind of web single page view. And then all the artifacts, which GitHub, you can save an artifact per workflow. In this case, these are smaller outputs that we were testing. They're only 16 megabytes each, but they're zip directories with folders of images. So through the web interface, you can also download the outputs from each of these processing runs. And again, this is nice for sharing with collaborators because anyone with a GitHub account can access these outputs, not only people with write permissions. So if you want to say, hey, around this analysis, here are all the outputs, you just point someone with a GitHub account to the repository and they can download the outputs from your workflow. Anyone who's not logged in can see this page, but will not have like a download button. And it's important, I think, to point out that these artifacts are only stored for 90 days and then they're wiped. So again, I think this is actually good. It's very easy with small research teams at the university, in my experience, to generate like a ton of data that then you forget to clean up. It clogs some server. Here, we're sort of enforcing this scratch usage. And then if you need to save something persistently, it's that next step to say, okay, this is something I actually want to keep long term. Let's save that to S3. When you're running these workflows, you can also get real-time feedback. So that's nice to make sure things are working as you expect. And the logs, just like the outputs, are automatically wiped after 90 days. The final piece in this puzzle, which I mentioned earlier, is this need to do an interactive analysis of the output. So for this particular study that I was emphasizing, this INSAR processing, we created an S3 bucket in AWS US West 2. That's where the CryoCloud Jupyter Hub is, and several other NASA-sponsored Jupyter Hubs are running in the US West 2 data center because that's where NASA data is being stored. And so we used CryoCloud to just read these outputs from that batch workflow to generate our final figures. And that sort of encompasses, I think, like the full workflow that this group was using. Some notes on scaling. So there are some what I would call major limits to using this for batch computing. The first two we didn't have any trouble with. The maximum workflow duration is 35 days. I can't think of one that would need to be run that long or what you'd be doing with it, but it's pretty long. A single job can run for 6 hours. And as I mentioned earlier, this was kind of a computing pipeline where the task is CPU intensive, but it takes about 10 minutes on a laptop, which is kind of the atomic like computing reference that I think most people have access to. And the maximum duration of that job would be 6 hours rather than 10 minutes. So again, that wasn't a problem for us. This one is the trickiest one. The max job matrix size is 256. And this was a bit of a challenge. So for us, as I mentioned, we wanted to logically structure these workflows so that one workflow was 1 year, and that would map out to as many image pairs as you needed in a year. And the job matrix seemed like the logical choice for that, but it causes you to have this limit of that's fine as long as the number of image pairs you need to process is less than 256 if you use that structure to how you're going about this. There are some alternatives. But what's nice about the matrix job is that you get kind of a single report for one workflow. And we really like that. So the screenshot I was showing earlier of going into GitHub's user interface and seeing a single workflow with all the image pairs neatly tucked underneath it is because we use this matrix job approach. So just to be aware of that, that's a pretty significant one. And then the concurrency limits depend on the plan you're on GitHub. So for anyone on GitHub, you have 20 maximum VMs that you can run through GitHub Actions, which is quite a lot, actually, in my opinion. And then for academic groups or anyone with the GitHub team organization, that goes up to 60. And then I'll get into this a little bit earlier, or a little bit later. There are some limits too if you choose to use larger machines. So there are alternatives that we considered where we thought we'd see if we could just do this on GitHub. And if not, we'd use some of these other systems that we've relied on for other projects to set up our own infrastructure. So those are kind of on the right, ones that we found very useful. In recent years, I would say are coiled, SciPy, and Runzon is an interesting system where you can more easily run GitHub Actions on AWS if you want. So if you want to use larger machines for any particular workflow, like if the base GitHub Action runner doesn't work for the computation you need to do, that's where you need to use larger runners, which are charged. So we had the luxury here at the University of Washington to have access to an Azure account, and we linked our GitHub organization with this Azure subscription. And that way, when you run any particular workflow, you can select the size of the virtual machine you want that workflow to run on. And also, because we're an academic organization through GitHub Education, you can confirm that you have an academic or research affiliation. And any organization that you own, you can promote to a GitHub team level. So as I pointed out earlier, that makes this more appealing because you have higher limits. So we went from 20 concurrent VMs to 60, and that's cutting down our total time to finish this stuff by a third just by doing that. The larger machines, I don't know how recent this is. This may be a little bit dated, but you have access to quite large machines for single workflows now. So up to a machine with 96 cores. For the example I was showing, we're depending on software that's not really taking advantage of a machine like that. It's not really optimized for multiple cores, and it's not really well set up to run multiple jobs on a single large machine. But looking at this table, you can easily see that you have access to some pretty large machines. And the nice thing about using GitHub as an interface rather than Azure is that these are simply like a radio button selection. You don't have to configure your own virtual machines when you're using the system. The costs are kind of approximately linear scaling too. So if you do have code that takes advantage of a 64 CPU machine, then you can get things done faster at the same cost. So that's also important. There is a markup. So most, if not all systems that do batch computing that have some managed infrastructure add this markup as far as I'm aware. By using these machines that are pre-configured by GitHub with the right operating system and everything. It's about a 7 times markup compared to setting up your own Azure, self-hosted Azure runners. So that's another thing to be aware of if you're concerned about the budget. And again, this is maybe dated now. I don't know if these prices have changed over time. I probably looked at this when we started or updated it like a year ago. So just to be aware of. If you are a US researcher and don't have an Azure account or don't have a cloud account that you want to connect to for this sort of work, I did want to make a pitch for this Cloud Bank program through NSF. So any US researchers or educators can apply. It's a quite short application now through Access, which historically was for HPC systems and now includes the ability to get yourself a account on major cloud providers, so Azure, AWS, or Google. So I think the cloud and these cloud resources are a bit more attainable than they have been compared to, let's say, 5 years ago. And honestly, just knowing how to get access to an account was very complicated. And that's it as far as the slides go. I'll just recap and say that I've found GitHub Actions to be surprisingly capable as a batch computing framework that's really well suited to small academic collaborations. I think it's a vastly more user-friendly on-ramp to batch computing than starting with a cloud portal and using Azure Batch or AWS Batch. So we've found it quite useful for a variety of projects. And then this ability to connect to an Azure account gives you quite a lot in terms of scalability. Finally, just as a reminder too, I would love in our discussion today to hear a bit more about what other people are using and whether or not they've tried any similar approaches to using GitHub Actions, or if not, what other systems you're using. I'll also just point out in the slides, but I didn't want to take up too much time. We included some additional resources. So there's a SciPy workshop from 2024, led by my colleague Valentina Staneva at the UW eScience Institute, that if you're new to this topic of GitHub Actions, is a great resource. It's a 4-hour workshop, so it goes over things much more slowly and has a lot of nice examples. And then there are a few other examples from projects that we've been working on here that you can explore at your leisure. One is predicting snow depth using data, public data inputs from Planetary Computer. And there's also a bit of information on running some workflows against these GPU runners if you have access to those. So in particular, one that looks at doing a training a PyTorch model on one of these runners, like a T4 GPU, to predict stream flow. So there's some nice examples that are in the slides if you want to explore later, if the one that I went over in more detail didn't grab your attention.